what's the first part of the question? What's the smallest number of coins that might be placed in a game of HT2, including the final coin that causes a player to lose? So what's the shortest game? Well, okay, let's just try and play the shortest game that we can. I guess Alice would go first, maybe with an H. Then, okay, can Bob lose now? No, because this will be the first pair, so it couldn't duplicate any previous pair. Now, from what we said before, what if Bob plays an H? Then we've got a pair of H's. And so can Alice lose now? Yes, Alice can lose now by playing H. So that's probably the shortest, I would say, because, well, if you is what we're trying to say. Let's rule it out by starting with the lowest number and rule them out one by one. Obviously, if it's just one coin, no, you can't lose that, and so that can't be the answer. If you put down 2 coins, then you can't lose either, because that's the first pair, as it were. With 3 coins, now you've got 2 possible pairs. There's the first pair, and there's the second pair. Whoops, that's gone off the bottom there. But you've got the first pair and the second pair. So, is it possible to lose? Yes, it is possible to lose, because we've got an example here that shows that it's possible to lose with 3 coins, and we've said that it can't be possible with 2 coins. So I guess that means the answer to the first one is 3 coins. Now the next one's a little bit more difficult. What's the largest number of coins that might be placed in a game of HT2? So how could you make a game, is the way that I think about it, so that it just keeps going on for as long as possible? I guess the way you do that is by every time someone puts down a coin, you come up with a new pair of H's and T's that hasn't been seen yet. So until eventually you're going to run out of pairs of H's and T's, and you have to duplicate a pair that's been there before. So, okay, then the question is, how many different pairs of H and T are there? How many different sets of 2, ordered sets of 2 pairings of H and T are there before you run out of them? And I was going to say if you've been doing computer science, but I guess also if you've got a maths background, this should be starting to ring bells. You know, sequences of H's and T's written down might seem, okay, a bit analogous, a bit similar to writing down sequences of 1s and 0s. So you might think, oh, hang on a second, might see, you know, some knowledge about binary numbers might be helpful. But even if you don't know anything about binary numbers, you can still work it out from the first principles. So maybe the best way to think about it is, okay, we're talking about pairs. The first of each pair is either going to be H or it's going to be T. So there's 2 possibilities. So we've got H or we've got T for the first one. There's 2 possibilities. And then we've got, for the second in the pair, we've also got 2 possibilities. We've got H or T. So it could be HH, HT, TH, or TT. So in other words, that's 2 times 2 is 4. There's 4 different pairs. So, okay, if there's 4 different pairs, can we have a game where we just go through those 4 pairs, and then whoever goes next is going to have to lose, because whatever coin they put down is going to form a pair that we've already had? And my intuition says yes. So let's try and check it with a game. So actually, let's just use this example here that we've already got. So we've got HH, that's the first one. HT, that's another one. TT, that's the next one. And TH, that's the next one. Well, hang on. That's all 4 pairs straight away there, because we've got the first pair, the second pair, the third pair, the fourth pair. So we've exhausted all 4 possible pairs, all 4 pairs that we had down here. So whatever situation, if we'd had a game that was this long, because we've had 4 different pairings, and there are only 4 possible pairings, they must have been exhausted. And so whoever goes next, which is going to be Bob, is going to inevitably lose. So actually, this game here is an example of the longest kind of game that you can have, I think, because it's been through all 4 possible pairings. And so then you just got this 1 extra one to ruin it. So by this length, which is how many? It's 6 coins. Then at that point, you've got 5 pigeons, which are the pairs, with the pairs that you've seen in the game. But there's only 4 different pairings that are possible. So we must know that 2 of them are duplicates. So someone's lost at this point, which you can see here. So yeah, maybe the answer to this one, 6.
People in chat are suggesting variants on either choosing to do what Alice does or choosing to do the opposite.
Okay.
Have you got a take on that?
Well, yeah, I've got a take, but maybe we should just try some out and kind of go through the process of see if we can figure out what it is from a reasonable starting point. So yeah, maybe let's try seeing what happens if we just always play the same as Alice. So okay, let's just say that Alice goes heads to start with, and then we're going to go heads as well because we're doing the same as Alice. So we're just trying out the strategy, see what happens. And then okay, if Alice plays heads, then we've won because Alice has lost. But so okay, we can assume that Alice doesn't play heads. So Alice, we only need to consider the case that Alice plays tails next, because if Alice plays heads, then Alice would have lost. So then, okay, so we're playing the strategy of putting down the same as Alice. So okay, let's go T again. Now, yeah, for the same reason here, Alice isn't going to put a T. Well, if Alice put a T, then we've lost, so that's fine. We don't need to worry about that case. So let's just worry about the case where Alice puts down an H. Oh, well, we've kind of run into a wall. We can't carry on with our strategy anymore, because if we put down an H, then we've lost.
Yeah.
But I guess that's because let's just see what happens. Can we win anyway? So we can't put down H, so I guess we put down a T. No, we haven't. That's repeating the HT from before. And I guess I realised just a split second before that we've reached 6 anyway, which means we've lost.
Yeah. The sixth move is sort of cursed, isn't it?
Yeah.
We've proved before that if it gets there, the game's going to end on this turn.
Yeah.
It's Bob's turn then. Okay, so this strategy, which was, I suppose, we started thinking about the strategy, play the same as Alice's last move.
So you can't, yeah.
Yeah, and then maybe improvise or something towards the end. That didn't work. Alice could beat us with that strategy.
Okay, so maybe let's try. What was the other strategy? Play the opposite of Alice. I guess we can give that one a go.
Yeah, sure.
Okay, so Alice, let's say, starts with H. Then we play T because we're doing the opposite. Now that gets more difficult now because Alice could play H or T. So, okay, maybe let's branch out into the 2 different possible worlds where let's first of all try the case where Alice plays an H. Now, if we're just going to play the opposite, then we're going to lose because that's another HT pair, which we've just had, so we would lose. So, okay, I guess in this case, we've run out of this strategy and maybe we'll just have to play the opposite until we can't. So let's improvise. We can't play T again, so let's try an H. Now, what can Alice do? Alice could play an H, but that would double the 2 H's we just had. Or Alice could play a T, but that would double the HT that we had at the start. Okay, so in this case, if Alice plays an H on Alice's second move, then we would win. So, okay, in that case, let's just see what happens if Alice plays a T. We've said we're always going to play the opposite, so I guess here we'll play an H. Now let's think about what Alice would play here. If Alice plays a T, that duplicates the HT that we've had there, but Alice could play an H, and then we're dead because we've had 5, so we'd be putting down the 6th one. Okay, so this strategy doesn't work either. I guess we could have played a different one here. Oh no, we couldn't, because if we'd have... Is that us? Yeah, that was us. Because if we'd have put down a T, we would have duplicated the TT. Okay, so interesting. Neither of the simplest strategies of just duplicating what Alice has done or doing the opposite of what Alice has done has worked.
I'm going to draw a tree up here.
Oh,
Or are you coming up? I'm
sounds exciting.
scrolling up. Okay.
Yeah.
So I think we've had a little bit of without loss of generality or something, but I'm finding that quite confusing. So I'm going to say
Sure.
maybe Alice plays heads, or maybe Alice plays tails.
Yeah.
Okay. Bob's
So I
go.
guess should we try just the top branch? So if Alice plays H, then
Uh-huh. So we could have Bob's rule here being play H. If you see Alice do H the first time, do H this time. That could be Bob's rule for this case.
yeah.
Maybe this goes wrong, and we'll reconsider that policy later.
But yeah,
it
let's
seems to be-
explore this branch and see what
let's
happens.
explore
Yeah.
and see what happens. So it's Alice's turn again. Alice could go H, in which case Alice loses. So probably not going to do that. Or Alice could do
I'll
tails.
put a green tick for that
Yeah, that's pretty nice.
because in that case we're sorted. So we just need a tree that always ends in ticks.
Sure. Yeah. Okay. Okay. So what do we do if Alice started heads and then for some reason we went heads, then
Yeah.
Alice went tails? What do we do in that case?
Well, if we went heads, that could put us in a difficult position because we've already had HH and we've already had HT.
Right. We've already had HH, and we've had HT. Okay. So this looks pretty strong now. So
Yeah.
if Bob does H here,
Hmm.
then the current set is HHTH, and then yeah, I agree. It doesn't matter what Alice does. Alice could go heads or tails, and both of those lead to Alice losing. Okay, so this looks pretty good for Bob's strategy. So Bob's strategy, if I had to say it in words for this first case, is something like, if Alice does H at the start, you don't have to think anymore. Make both of your moves H, here and here.
Nice.
And then whatever Alice does, all of these cases for Alice afterwards, then Bob's gonna win. So this is a good strategy, I think. We've also got this tails case.
Yeah. So let's see if we were right. And if the strategy here is, okay, if Alice plays tails, then we just play tails both times.
And the thing I think Isaac's been trying to convince me before, and I think I'm buying it, is that we could just swap all the heads and tails on this branch, and it'll still make sense. Let's see if I can do that. So tails, Alice loses. That's still true. Green tick. Heads here, I guess here if I'm swapping all the heads and tails, then I get a tree over here. Where...
So yeah, does Alice lose in both of them? TT we've already had, TH we've already had, yeah.
Yeah, okay. I think I'm coming around to this idea that if you can flip all the heads and tails so that whatever Alice's move was. But you probably got, if you're explaining the strategy to Bob, you've probably got to mention that as well, right? So that Bob knows about the heads tails swap.
Right. Yeah.
Cool, okay. So our strategy is something like...
just keep playing whatever Alice plays first.
Yep. Play whatever Alice plays first.
So if you suppose N is odd, and Bob chooses to play by always duplicating Alice's previous play, and Alice knows that that's what Bob's going to do, show that Alice can always win. Okay, so in this case, we can assume that Bob is always just going to do whatever we do if we're Alice, and we need to always win. What's the simplest strategy? The simplest strategy is just Alice just plays the same thing every time. I have an inkling that this is going to win.
Right.
And if that's right, then that's not so exciting. Maybe we should try the tree, just to see if that would lead us to the right answer. But I guess it's a bit difficult to draw a tree when we don't know what N is. So maybe should we see what happens if we just try?
Okay, so is this a strategy that you just thought of? As, like it's sort of a strategy in words, right? Like
it's just this one's a strategy in words. But the reason I'm feeling hopeful about it is.
Sorry,
Bob is going to. By all means, write it down. Yeah, Bob is going to run out of. What am I trying to say? If you just keep putting down H's down, then the first N are going to be all H's. So whoever puts down the first N isn't going to lose, but whoever puts down the next H would lose. Because, okay, maybe it's easier to draw with a diagram. So we've got like H, H, and then H. So that's the first N. But then if someone puts down another H, then that's another N H's. And so whoever puts down this loses. So I guess the question is, who's going to put down that N plus first H? That's the crucial question.
That's the one that you've labelled, labelled lose. It's the N plus 1th heads. Is that one of the ones that Alice is doing because she's locked into playing heads only, or is it one of the ones that Bob does because Bob has committed to copying Alice?
Yeah, well, I guess we know that N is odd.
Yeah. We've got this fact in the question, haven't we? So
that's helpful.
that helpful, relevant, in the right place in the question. Lovely. N plus 1 is even. So this is one of Bob. Bob has lost, I think.
Well, okay, what are the ways that you could be certain that it's going to be finished? Well, one is if they've exhausted all the sequences of 6. If all the sequences of length 6 of heads and tails have come up, then someone's going to have to lose.
Right.
That seems promising.
That's the pigeonhole principle thing.
Oh yeah, the pigeonhole principle again.
Yeah. So if there's only a few possible matches, a few possible sets they could have, then maybe they'd be forced to get through all of them in 2 hours. How many of those are there? I guess there's 2 to the 6 possibilities for what a string of 6 things looks like. 2 to the 6 is 64. Is that right? 2, 4,
yeah,
32, 64.
Yeah, that's right.
So am I done? Are they done before? Are they done because they're going to run out of combinations of 6 things to play?
I think that's right. Yeah, I think that's right.
Okay.
I guess
is that the same argument as part 1?
Yeah, I think it is. Yeah.
Do we need to think about how they play these, or?
I don't think so because of the pigeonhole principle. I guess the one thing to say is it would be 65 because it's when 64 you exhaust all of the sequences. Oh, hang on, no, that's not even right. I think we have to be a little. I think it's quite safe actually because 64 is a lot less than 120. But I suppose it's just interesting to be exactly right because the first 5 plays don't give you a sequence of anything, and all the plays after that introduce a new sequence of length 6.
Oh right, okay. So I guess the number of sequences. I can start by having my sequence start on the first one, or I can start by having it on having my sequence start on the 65th one. So I need 70 coin flips to pull off this 64 brackety thing.
Cool. So yeah, show that if Amy starts by playing either 1 or 2, then Brian can immediately win. Oh, that makes sense. That seems quite straightforward. Because if Amy plays 1, Brian can play 2, which gets to 3, which is a multiple of 3. And if Amy plays 2, then Brian can play 1. And that's allowed because Brian can play any of the numbers that hasn't been done so far. That's a nice, easy one to get started.
Checking that we've understood what Brian's allowed to do. Yeah, different number, add up to 3. Good. Okay.
Yeah. Great. Suppose instead Amy starts by playing 0. Show that Brian can always win within 2 rounds.
So a round is each of them playing a number, right? And
I think that's right. Yeah.
No other game relevance. It's just counting how many things have been played, I think.
Yeah, I think that's right.
Okay.
So maybe we should try and draw a tree of the different possibilities.
Maybe do the tree this time.
Sure, yeah. Trying to scroll down?
Yeah, I'll scroll like that.
Yeah.
Okay.
Okay. Maybe I should pick a different. I'll just go with black. Okay. So Amy goes with 0. So Brian is going to either, well, it can't be 0, so it's either 1 or it's 2. So let's start with Brian playing 1 first. Then what can Amy play? Amy can play either 0 or 2. Can't play 1 because you can't play the same thing twice in a row. So now, can Brian win here? Well, we need to take it to a multiple of 3. So if Brian plays 2, then the total is 3, which gets us to a multiple of 3, so that works. And if here, we've got the total so far is 0 plus 1 plus 2, so Brian can just play 0, and in both of those cases, we get to 3, which is a win for Brian. So then we've got to go back. Actually, we don't even need to consider this branch now because we can just do this one.
Yeah, maybe Brian can win by doing a 2 as well for variety or something. But I think
Doesn't matter.
Now that we found this winning bit of branch based on Brian's decision, don't consider her doing anything else. Yeah.
Okay, so I guess we're doing a similar thing. So if Amy starts by playing either 2 or 0, then Brian can immediately win. I guess that's pretty similar. Then Brian can just do either. Brian could just play a 2 or a 0.
Sure.
And 2 is 1 less than a multiple of 3, so Brian would win straight away. Nice. Okay, what if Amy starts by playing 1? Explain why it cannot benefit Brian to play 2, assuming Amy plays with the best strategy. That is an interesting question. Yeah, because I guess you've got to decide what it means for something to benefit Brian.
So I guess the way I'd word this is something like, if Brian plays 2, then the total so far is 3, and that's like resetting the game. Before we started, the total was 0, and now it's 3. It doesn't feel like that's changed anything, I guess, in terms of, I mean, it's changed the total. The total's up by 3, but it hasn't changed whether the total's 1 less than a multiple of 3 or not.
Yeah, it hasn't changed the total modulo 3. In other words, yeah, it hasn't changed the distance from a multiple of 3. Yeah. But there is one difference, which is that if Brian plays a 2, then Amy can't play a 2 next round. Whereas
right.
At the start, Amy could have played 2. So that's something else that we need to
so we're not quite exactly back to the start of the game because now Amy's banned from playing 2. Okay, so we've got...
but if Amy were to play 2...
Yeah,
Brian can play 0.
maybe Amy doesn't want to play 2 anyway.
Because if Amy plays 2, Brian can play 0, and so Amy wouldn't play 2. Or if Amy does play 2, then it's to Brian's advantage.
Okay.
Oh yeah, so that's why we need to assume that Amy plays with the best strategy, because Amy wouldn't play 2.
I see. Okay, right. So, summary. If we assume Amy plays 1, then suppose Brian plays 2 next. Well, that's back to the start of the game. The total is 0 more than a multiple of 3. So later on, we're going to have to win from this position if we're Brian. Amy's playing with the best strategy. That means Amy's not going to play 0 or 2 next, because we've seen that then Brian would immediately win by playing 2 or 0.
So it doesn't matter though. It's
Amy's going to play 1 again. So what's the benefit? We've gone round in a circle. Our total is now 4. From Amy going 1, Brian going 2. Amy's playing with the best strategy. I don't know what the best strategy is, but the best strategy does not involve playing an illegal move or losing on the spot. So Amy's going to have to play 1 next.
Yeah.
So Amy's only legal move that doesn't cause Brian to win straight away. And now Brian's back where we were before, right? You've got Amy's just played a 1, so you're not allowed to play 1. The total is 4, which is 3 more than it was before.
But it's not any easier to get to her. It's exactly the same in terms of the difficulty to get to her.
I suppose there's one final thing to say here, which is Brian hasn't achieved very much by doing this, except Brian's wasted our time.
Yeah,
Brian
that's
has
true.
Brian has,
Close
which
to
is
the end of the
relevant,
game.
right? Because
Yeah.
at the end of the game, if this keeps going on for too long, then Amy wins, right?
Right, yeah, that's right.
Okay, so this thing is relevant in this because it's not in Brian's advantage to delay the game. Brian
Yeah.
doesn't win the long game that goes on for 10 rounds or something, because after 5 rounds, Amy wins. Okay.
Yeah.
I was
that's
wondering
right,
when
yeah.
that was going to become relevant, right?
Yeah.
Okay.
Yeah, so in short, there are 3 things that change, but none of them matter. One of them is that the number is increased from 1 to 4, but it doesn't matter because the distance from we're talking about distance from multiples of 3. One of them is that we're 1 turn down, but that's not to Brian's benefit because Brian's going to lose. And the other thing is that Amy's band wouldn't be able to play 2, but it doesn't matter because we're assuming that Amy's playing the best strategy anyway, so it's not to Brian's benefit.
Yeah. What on earth next?
Okay, so I guess Amy can either play 1 or 2.
Sure.
Well, 2 is going to be no good. Because if Amy plays... Oh, no, hang on. I'm still thinking in the game where it was getting to a multiple of 3, but it's 1 less than a multiple of 3.
Yeah, I think Amy.
Oh, even so, it's still no good, yeah.
Amy is allowed to play 1 or 2. I'm reading Brian's win condition carefully, sorry. Brian wins if after he plays, so Brian does have to play a number.
Yeah.
Okay. So, suppose Amy plays 1. So A is either going to play 1 or 2.
Yeah.
If 1, then we've got 1-0-1. And I think Bob can win now, right?
Oh, by playing 0.
Yeah. Because then the total is 2.
Yeah. Nice.
Bob wins.
Yeah.
I think my advice for Amy, I don't know if this works out long term,
Well,
but probably play 2
yeah.
now.
Yeah. Well, I mean, we've shown that that's... If it doesn't work out long term, then Amy loses long term because this is the only strategy that has any hope.
Yeah, sure. Okay, this is the only hope. I like that.
Maybe.
Only hope. Because we're about to think about people playing with the best possible strategies. Who's going to win the game?
Well, hang on. Oh, yeah, okay. I guess I was going to say what would happen. Like, could Brian win immediately or something? But I guess it doesn't matter. We've just shown that, well, 1's no good, so 2 is the next thing that Amy should do, yeah.
2's the only thing left over for Amy to consider. Let's think about that case. I think it might answer part 6, but I just want to find out what happens next. I feel like we're really getting into Amy and Bob's minds now.
Yeah.
So they've played this start. This is the best start for Amy. This is the only real good start. Yeah, I'm not happy really about this phrase best strategies, but assuming that it's not lose immediately, Amy has to start with 1. Bob's going to go 0 because Bob's worried about the game going long. Amy is then going to go 2 because it's Amy's only hope. Bob is faced with a problem now. Bob can't win immediately.
Right, because that would be putting down a 2, which Bob's not allowed to do. So it's either 0 or 1.
Right, Brian. Sorry.
Oh yeah,
I started that. Okay. Brian could do a 0 or a 1. Brian's going to consider both of these possibilities and think carefully.
Should we scroll down a bit?
Yeah. Sorry. Oh yeah, I'm off the bottom. There we go.
Nice.
I'm getting into this now. I don't know who I'm supporting, but I think I want Amy to win the long game. I think that's what I want.
Yeah, it does seem a bit hopeless for Amy, doesn't it?
Yeah, Amy's lost so many cases.
Okay.
In particular, I think if Bob says 1, then I think Amy could go for a 2 next. I quite like that because I quite like this 2 here for Amy because it puts it back to a multiple of 3, so Bob can't win immediately. This feels like if Bob goes down this route, 1, then Amy might do Amy might say the number 2. This feels like a waste of Bob's time.
Yeah,
I don't
for the
want Bob to
sake,
win.
it feels like it's gone back to the previous one. It feels like it's gone back over here.
Yeah, like what we said before, right? That you're now banned from playing 2. So Bob's now going to move. Bob's banned from playing 2, and the total is a multiple of 3 again. So Bob can't win immediately. Isn't allowed to say 2. Bob over here would be thinking about, in this case, we're thinking about 0 and 1. I think this just means that Bob should not go this direction. This is not interesting for Bob.
Yeah, I agree with that. So Bob's not going to do that. That's not in Bob's interest.
Waste of time. Okay, let's write out a new one.
Okay, so assuming Bob's playing the best strategy, which is what we are assuming, so Bob must play 0.
Okay. Amy's turn. Oh, feeling bad for Amy here. We're looking at a multiple of 3.
Yeah, but hang on, that's what the game was at the start.
Yes, true.
So could Amy just play 1 again?
Amy could do the 1 again. 1 again. Yeah, I think that's a good idea, right? Because it's going to force all of this
now
bit
Bob
has stopped counting. So now Bob's in trouble. It doesn't benefit Bob to play. It's like starting the game again, but we've wasted 2 rounds.
Yeah.
So Bob's probably going to play 0, and then we'll see the 2-0 come up again.
Yeah, so it feels a bit like this one goes back to here, and this one goes back to here.
Yeah, if we had some sort of finite state automatum to keep track of what state we were in, then we could go through like that. Cool. So I think this ends with Amy winning.
Yeah.
On time after messing around for a bit and wasting enough of Bob's time that we hit this rule about Amy wins if Brian's not won within 5 rounds. And in fact, the actual number 5 there, I think that doesn't matter. I think if the rule is Amy wins after 1,000,000 rounds, Amy can just stall for time by doing this sequence, where Bob kind of has to keep saying 0 or waste all the time.
The idea is you've just got one state, one circle that the machine is currently in, and it moves between them depending on the input that you give it, and it just follows the arrows. And S1 here has got 2 circles around it because it's the accepting state. And what that means is, if you give it a certain sequence of inputs, if at the end, after you've given it all that sequence of inputs, it's in an accepting state, so in this case it's the one with 2 circles around it, S1, then that's accepted by the machine. If it's not, then it's not accepted. So here it says, as an example, ABA is accepted by this automaton because you start in state 0, because that's what this arrow shows. Then you give it A, it goes to state 1, B, it goes to state 0, A, it goes to state 1 again. And because after we've given the full sequence, it's in an accepting state, then it's accepted. But, let's say that you gave it A, B, and just stopped then it's not an accepting state because S0 hasn't got 2 circles around it, so that wouldn't be accepted.
Yeah. So someone in chat has asked, just for clarification, what's the difference between an accepting state and a normal state? And I'll take that while you're following the arrows around, there's no difference between an accepting state and a normal state. It's just
that's right. Yeah.
States. It's just once you stop, you check whether you're in an accepting state. If you are, then your sequence has been accepted. So, for example, ABA would mean follow the A, start here, follow the A, follow the B, follow the A. Oh, and now look, I'm in an accepting state, so this is accepted.
That's exactly
it has
right.
kind of no gameplay relevance except checking where you end up. Okay.
Yeah, and then I guess the one other thing is just terminology. They call a sequence of inputs a word. So if we're talking about words in this question, then that's what we mean. So ABA is a word, an accepted word, and AB is a rejected word.
Okay, so what does this accept? We've seen that it accepts ABA, doesn't like AB, because after AB I'm just over here somewhere. It also looks like you can go wrong if you end up in S2, because you'll get stuck in S2.
Yeah.
Okay.
So how do you get stuck in S2 then? So I guess, so if you put a B straight away, then you have to end up in S2. Or if you go from S1 and you put an A.
So if it was going quite well, and
Yeah.
then you hit an A when you should have done a B, if you zigged when you should have zagged, then you get rejected to S2.
Right.
This machine
Yeah,
is like,
yeah.
no, you've lost my interest. You had me
Yeah.
with that stuff at the start, but you've lost my interest. Go and sit in S2. You are rejected, no matter what else you tell me after that.
Yeah.
So
Yeah, so actually, it looks like the only way to get an accepting word is just keep zigzagging between S0 and S1.
Yeah, you
And-
want to stay up here.
You want to stay up there, which means you have to just keep going A, B, A, B, A, B. And if you deviate from that A, B, then you fail. But also, you have to, the last one has to end up in S1. So the last one has to be an A.
Yeah, lovely. Okay, so we've got to have something like this with we can do AB as many times as we like, because that just loops us around. But we've got to end it off with an A, so that we do one last move to get to S1, land in S1, and then stop. If at any point you don't alternate the letters, if you start with a B, I suppose. If you start with a B, it's bad news. If you started with an A, but then did an A, bad news.
Yeah.
If you do AB, then the next thing you should do is A, and then a B. And then
Yeah,
a B.
yeah.
Okay.
I like that description of any number of ABs and then an A,
Yeah, okay.
because any number of ABs just gets you back to S0, and then in S0, if the last thing you do is an A, then you're good. I guess including 0 ABs. So yeah, maybe 0 or more ABs.
Okay, different automaton. We're going to swap the accepting and non-accepting states. Okay, that's mind-bending already. S0 and S2 are now going to be the accepting states, and S1 is not accepting. So does that just mean it's everything else, right?
Yeah, that feels
Like
like it's
everything
very
else.
likely to be true, but I guess we should.
Should we think about it?
I think that seems right.
I think it's going to be everything else.
Yeah.
I don't have a good description of everything else other than all of
Well, I think I think you can just say anything apart from that, right? That's pretty clear. Because yeah, if you do any of the things that before would have been accepted, then now you end up in the one state that doesn't accept it.
Yeah.
So that's the only way for it to not be accepted, is to end up in the state that before would have accepted it. That seems right to me.
I'm thinking a little bit carefully about. There might be like a special case for the word that has no letters in, but maybe that's just a sort of mathematician construct and not actually.
Well, I think no, that's right. Yeah, the empty word is you just stay in S0 and that's it.
Okay, so that is now good, and it was bad before. Okay, yeah.
It was bad before because it didn't have the A before. Draw an automaton that accepts all words containing an even number of A's and any number of B's.
Okay.
That's fun.
So any number of B's is telling me, I think, that if it sees a B, it should just not react to that. We should design this robot so that it's like, B, I don't care. So I'm imagining.
So I guess that means.
Okay. Yeah.
Yeah. So that. Yeah. So I was just going to say, well, I guess that means that it doesn't change state if you give it a B.
Yeah. Right. Okay. That's the finite automaton kind of language for it, I suppose. If you give it a B, it doesn't change anything. Okay. How are we going to get it to do an even number of A's? Okay, let's give it an input thing. I'm going to try and draw something over here. See if this fits on stream. I'm going to draw it not huge, but draw something over here. Let's give it an input state.
Yeah. Okay, so do we want that one to be accepting? I guess we do, because 0 is even.
Sure. Yeah. Okay. So if it gets the empty word, no letters, then this should be It should be accepting. There we go. Okay.
That's.
Okay. Then if it sees an A, it needs to get out of this state, because if it sees an A, then it's gonna the word might be A. So it's got to get out of here.
Yeah. So we need a new state.
Yeah, new state. I guess this is not an accepting state because I don't want A.
Yeah. You don't want A to be accepted. Yeah.
If it sees a B, then I could give it another state for the B's, but I think that the B just doesn't matter at all. So I'm going to loop the B back to here.
Yeah, that seems good to me.
Okay. What else? We need to decide what happens when it's in state 1.
Yeah, well, I guess a B doesn't make a difference, like you said before.
Yeah.
So I guess that goes back to itself.
I don't know if
So
we need
now-
a third state at some point, but I want
Well-
to draw these loops for B's everywhere. Just like B's don't matter. So if you see
Yeah.
B, if you see like a different letter of the alphabet, I suppose you can't for this question. But like, yeah, it doesn't matter.
Okay, yeah.
I really want to draw this looping back. I haven't even really thought it through.
Yeah, it feels right, doesn't it? Because
That's right.
okay, if we give it an let's temporarily put it in and see if it's right, and we can always remove it if not.
Okay. Have you got a different colour? I've got.
Yeah. Well, let's try.
Oh yeah.
Right.
Okay. Does that work? I feel like, so. I wanted to put it back because I wanted a squared or AA. Sorry, I wanted the word AA to be.
Accepted. Yeah.
Yeah.
I think that's right because okay, now if we have any even number of A's, we end up in S0, which is accepting, and if you have one more than that, then it puts you in S1, which isn't accepting.
Yeah, I want it to look. If it's just being given A's, then I want it to do this loop lots and ignore the B's. I think that's everything that it needs to do.
Yeah.
Yeah, I think that works. Okay, that's our answer for part 3. This automaton. So even number of A's or any odd number of B's, I think I can do this by tracking the A's and the B's separately. So I think I want states like this to track to count the A's, or at least count if it's odd or even.
Yeah.
And I'm going to have states over here that it swaps between when it sees B's.
Yeah.
Something like this.
That seems good to me.
So now I got to think about which ones I want to be accepting or not. But I guess I want it to take composed of what do I want? I want even number of A's. So I think I want this to be accepting. So that A squared is good.
And the corresponding S2, right? Because that's an even number of A's as well.
Yes, that's true. I'm a bit worried about the B's.
I think we're safe because it's or.
This is really good, right?
Yeah.
Or an odd number of B's. So over here I've got an odd number of A's, but if I'm over in S3, then at least I've got an odd number of B's. So this is accepting too. I don't want S1 to be accepting because if I'm in S1, then I must have an even number of A's to get over this side of the picture, and I must have an even number of B's.
The other way around, I think.
Oh, I must have an odd number of A's. Thank you.
Yeah.
If I get over to S1, if I end up in S1, it's because I had an odd number of A's and an even number of B's, which is exactly what I don't want. Okay.
Great. Nice.
Can you see an easier, obvious example, or?
No, I think that's right. I think you might be able to combine S2 and S3 into one state, which just has A looping back to itself. No, I don't think you can actually, because that loses track of the number of A's. Yeah.
I'm sort of getting it to track the even or oddness of the A's in a bit of memory this way, and I'm using a different bit of memory over there, and I'm a bit worried about squashing them. Anyway.
No, I think that seems good. Yeah. Great.
Speeding up. Okay. So then they've got some notation for this last part to say, think about all the words composed of some number of A's followed by the same number of B's. Okay. So that includes AB, and it includes, I'm not sure if it includes the empty word or not because we haven't been very clear about 0 here, but it includes
it has. It says where n equals...
Oh, 0 is included. Okay, so the empty word is included. A cubed, B cubed. Sorry, you're right. There is a 0 here. Now it's an accepting 0. A4, B4, and so on. Okay, that's L.
Yeah.
Okay, what's the question?
Suppose that we've got a particular final automaton that does accept precisely the words in L. So it accepts exactly this set of words. Show that if I is a different number than J, then the words I A's in a row and J A's in a row must lead to different states of A.
Okay.
And then hence show that this leads to a contradiction. So I guess that's two different parts.
Yeah, I've no idea about the hence, but I think no, go. So we don't know anything about the automaton. We don't know how many states it's got, how many accepting states it's got, or what the A's and B arrows look like. But we just know it accepts the words in L.
Yeah. Well, hang on. I think I've got a bit of an intuition for the first part, which is you must need to keep track of exactly the number of A's that you've had, because then you need to accept words that only follow, if you start from having B's from there, exactly the same number. So okay, if I A's in a row and J A's in a row led to the same state of A, then you wouldn't be able to. You'd have to accept either neither or both of the word those with IBs following and JBs following.
Yeah. So we'd have to look at. You could think about what happens next if we follow up our AIs with, I think you said, BIs.
Yeah, that must be accepted.
Yeah, we've got to accept this one, but we don't want to accept AI. We don't want to accept AJ.
Yeah, AR. Oh yeah.
AJBI.
Nice. Yeah, that's right.
We don't want to accept this one, because only one of these has got the same number of A's as B's. We want to accept this first one. We don't want to accept the second one. But if after doing this bit, if it's in the same state after doing these A's, then following the B arrows around, I times will lead us to the same state.
Yeah.
So if it's in the same state after these A's, then we'll do I many B's afterwards, and oh no, it's now still in the same state, which is either accepting or not, but it can't be both.
Yeah.
Okay.
Yeah. So either way, one of those it would give the right answer for. So we know that it must be in a different state, which is what the question is asking.
Cool. Right. Okay. So this must lead to different states of A. So this is a contradiction.
So the assumption we made must have been wrong. So there must be no finite automata A that accepts L.
Right. So why is it a contradiction? So why is this a problem for our finite automaton? I guess I think I can see why, but only because I read something in
finite.
Chat. Yeah, is this word finite? That we've shown it's got. If I really concentrate, we've shown it's got a different state ready for each of these AIs and each of these AI AJ for all the numbers.
Yeah, if it accepts L. Yeah.
So after you do A 37 times, it's got to be in a different state to when it's in after seeing 38 A's. Can't repeat any of them. It's a finite automaton. It's going to run out of states eventually. Problem.
Yeah.
Lovely. Okay, I actually quite like that.
Nice. Yeah, that's neat. Yeah.
Cool. Right. Okay.